Jai Hind. In today's lecture, we'll talk about adversarial search. The concepts that I'm going to cover here are the concept related to games, what type of environment will be there in games, and what type of research will be, what type of search will be used. Okay, and for this we will after discussing min-max, we'll talk about the pruning that can be applied on the algorithm. So, I'm starting with the multi-agent environment that are present in games. What are multi-agent environments? When we are given an environment can be deterministic, or it could be fully observable or partially observable, or the environment may be static or dynamic, or it may be changing with time. So, what the concept is, when we are having these different type of environment, we have to now consider that how many agents are working in that particular environment. So, here we are talking about the environment which is having multi-agents. Multi-agents, when we are having multi-agent, it means many agents are working at same time, and when many agents are working at same time, it means they are making some changes to the environment. So, if a particular agent we consider, the agent is working in the environment, plus the environment is getting changed by other agent also. Okay. So, when any given agent will need to consider the action of other agents also, that how that is affecting the environment, that is our multi-agent environment, in which we have to consider the working done by the other agent also. When we are having other agent also, so we cannot predict what work has been done by that agent, so that will create changes in the environment. When we are talking about multi-agents, the multi-agents may work in competition or may work in cooperation. When, let me say, there are 2-3 robots. The robots are the agents, and they are working in an environment and picking some box which cannot be picked by just one. So, that is cooperative environment. When one agent is working in adversary to another agent, then it is competitive. For example, games. Okay. So, competitive environments in which we use or we require some different type of searching, that is called adversarial search. So, these problems are called games. So, what we are having? Competitive environment here. So, now let us discuss our concept. So, now we will talk about what is the relation of games to search. When we talk about searching, in searching there is no adversary. So, let me take a search without an adversary. So, when we are searching something, so actually we are finding a goal. A solution is to find the method to find the goal. We use heuristic techniques to find the optimal solution to reach to the goal. For example, we are planning some path. We have to move from one city to another. So, we are planning path, or let me say some processes are there. So, we have to schedule the activities. We have to schedule the processes. When we are saying that we want a good solution, the best solution for path planning or scheduling activities, so it means I need some function to evaluate the cost. So, evaluation function is used to estimate the cost from start to goal node. Start node to goal node. Now, what is there in games? In games, we are having adversarial environment. There is adversary. One person is playing, one agent is playing, other is playing in opponent. Other player is the opponent. If one will make a move, the other will try to degrade its move, or other has to do something that will make him or her win and other to lose. Okay. So, what does it mean? It means it has to nullify the other's move. So it means a strategy is required. Okay, so when somebody will make a move, let us take example of chess. When one has to make a move, one agent, naturally it will be the current condition of the chessboard on what basis it will make the move. So what will be the evaluation function? The evaluation function will evaluate the goodness of game position, where the game has arrived. Okay, so we can use as we are able to relate the strategies and the evaluation function, so we are able to apply searching to game. This is called adversarial search. We'll talk about now the game setup to understand the concept of adversarial search. So our game setup is we are assuming two-player game. The two players we are naming here max and min. Max will make the first move and then the turn will go to the second one. Second is min. After min, again the turn will go to max. It will go on working on making the turns. Turns will go on changing until the game is over. Okay, so how we will find out that who has won? Okay, so winner will get award and loser will get penalty. Okay, so what we are having? We are having some initial state. From initial state, we will make some moves and we will reach to the winning state. When we are saying that somebody has won, it means the other one has lost. But there is one more category, that it may be the case that the game has been drawn. It means it's not only win and lose. There are three situations: win, lose or draw. Okay, so our initial state will be, let us take the example of chess. Initial state will be the board configuration of chess. Now what will be the successor action? We know we are having four components to define a problem. First one is the initial state. Second is the successor function. The successor function is the action. Third one is the goal test, which we are calling here terminal test. And last one is the path cost. Here we are not using path cost because we are using the searching in adversarial situations. So we will use the utility function. The utility function will assign a numerical value to the terminal states. If the terminal state is having the value +1, it means it has won the game. -1, it will lose the game. And 0 means it will draw. The game has been drawn. Let us try one example, that is of tic-tac-toe. So what will be the initial condition of the tic-tac-toe? We are having 3x3 board, checkboard. All the cells are empty. So we have make the setup that the first turn will go to max, then to min, then to max, then to min, until either the draw condition is there or the win condition is there or the lost condition is there. So if we consider this game now, the initial configuration is this. Now what max will do? Max, as we are playing the game of tic-tac-toe, so what max has to do? Max has to put its symbol in one among these 9 cells. So let me take X symbol for max and not symbol for min. So what max will do? Max will go on putting symbols X and min will go on putting symbol O, not symbol. What will be the winning condition? The winning condition will be either X is in same row, same column or diagonal, and if knots are in same row or same column, then it means max has lost the game. It means min has won the game. So initial position is max is having all the cells free. Now what is there? We are going to make the tree. What is the possibility? What possibility is there for max? Max has to put X, so it is having 9 possibility. It can be put on in first cell, in second, third, or second row first, second row second. So 9 options are there. So we can have 9 child nodes, 9 successors of the initial configurations. Now let me say max put it in this situation. First, now turn will go to min. Max is having these options. So we can have any option. So let us explore the first one. In first one, Max has put not in the first cell. Now what is left with min? Min is having now 8 options. 1, 2, 3, 4, 5, 6, 7, 8. Not can be put in any of these 8 positions. So there are 8 cases. In the first one, second one, third one, fourth one, and so on. So how many options are there? 8. Now turn will go to Max. Now 2 has already been used. Now what min will have? Max will have? It will have 7 options to put cross. Then min will have 6 options to put not, and so on. Now after going like this, one case will happen. What is that? Let me consider this one. In this, what is there? We are having 3 knots in one column. It means Max has lost. Max has lost the game. If we consider this situation, in this, the draw condition is there. No X's are in same row and no knots. Okay, so draw condition. So utility will be 0. If we consider this, X are in diagonal form. So this will be +1. It is showing that Max has won the game. So we are having number of options. It will be a very lengthy game tree. So this way we go on drawing the game tree. The partial game tree is shown on this particular slide. Now what strategy we are taking? We are finding the contingent strategy for Max, assuming an infallible min opponent. Both are good at their game. So what is our assumption? Both players are playing optimally. So given a game tree, the optimal strategy we have to find out. The optimal strategy can be determined by using the minimax value of each node. So what we will use? Minimax value. Now what is minimax value? Let me say n is the node. What is minimax value of the node n? If n is terminal node, what are the situation? Either it will be terminal node, or it will be max node, or it will be min node. There are 3 situations. So if it is terminal node, then we will take the utility of the node. Okay, if it is max node, what max node will take as the value? It will see all the successors. It will find out all the successor. The successors value are given. It will find out maximum among those. And what min will do? Min will find out the minimum min-max value among the successors. We are having, so we have given here the recursive definition. The minimax value of n is the utility. If n is terminal, it is maximum value among the successor. If it is max node, it is minimum value among the successor. If it is min node. So how does it work? Let us understand that. We perfect play for deterministic perfect information games. So here what is shown, the 2-ply game. 2-ply game is there. So we are having max and min. Max will get the first turn. Min will get the second term. Then again max until we get the solution. So it's a 2-ply game. So what is the idea? Choose move to position with highest minimax value. Which path we will follow? Which steps we will take? We are given the game tree, but we will find out the game tree. We will select the value, game tree, game branch, which is having the highest minimax value. So now let us consider it. How does it work? This is these are the utility values assigned to all the nodes. So we are having ply games in which I am having 1, 2, 3, 4, 5, 6, 7, 8, 9 terminal nodes. Now Max has to decide what action will be taken here. Will it take action 1, or it will take action 2, or it will take action 3? As we have seen on the tic-tac-toe game partial tree, the Max initially has 9 options. So now the question is, which one will be selected from the 9 options? That we are explaining here. We are trying to understand with help of this particular game tree, a smaller game tree. Here the 3 actions are possible. So what will happen? Max will calculate the maximum among these 3. When it will consider the maximum among these 3, it means it has to calculate the minimax value of all 3. Now this is min's turn. Okay. Now what min has to do? Min will select the minimum value. Okay. So it will see the successors. Successors are terminal nodes. So min is able to calculate the min value from the terminal nodes. Okay. Max couldn't do that because the successors of Max were not terminals. Okay. So it will calculate this value. Here, which term is this? Min. So what min will do? The values are 3, 12 and 8. So minimum among these is 3. Okay. So Max got 3 value from here. Now it will take for action decision for action 2. Now again it has to calculate the minimax value of this node. Now turn goes to min. Now min has to select the minimum among these values. So what are these values? 2, 4 and 6. The minimum value is 2. So 2 will be selected. Okay. Now Max has to search for A3 also. So it will calculate the minimax value of this particular node. Now again the turn goes to min. Now what min will do? It will see the successors and will take the minimum value. What is the minimum value here? These are the utility values. The Max is trying to maximize the utility and min is trying to minimize the utility. So what min will do? It will calculate the minimum value from here and will take that. So what it has calculated, the minimum value is 2. So it will assign 2 here. Okay. Now Max has min values for the success, minimax values for all the 3 successor. Now what Max will do? Max will calculate the maximum among these. What is that? 3. So 3 has been selected. So now how will Max decide that which action should be taken? It will see that from where it is getting 3. From where it is getting 3? From this action 1. So it will perform action 1. Now what min will do? Once Max performs has performed the action 1, now turn goes to min. Now what min will do? It will perform the action A11 because that is giving the minimum utility. Max is trying to maximize the utility and min is trying to minimize the utility. So actually our game setup is that we are giving first turn to Max. Max is trying to maximize and the opponent is trying to negate that. So that maximizing and this is minimizing. It will try to minimize the value. So this is our minimax algorithm. Minimax 2-ply example. Now if min does not play optimal, what we have considered there? We have considered that Max is taking the best among successors. Same way min is also taking the best among the successors. Okay, there the best is maximum and for min the best is minimum. Now what happens if the other player is not playing optimally? Definition of optimal play for Max assumes min plays optimally. So maximizes worst case outcome for Max. It means it will try to negate as much as it can, or it will try to minimize the utility as much as it can. Okay, so this is the worst case. So designed for worst case. So when it is designed for worst case, naturally if it is not playing optimally, then it will do even better. So this is our algorithm. What is the algorithm? We have to take the decision that which action to be taken. So we are given the current state and we have to decide the action. So inputs are our states and the current state in the game. What minimax decision will be? Initially the turn is of max. So that's why we have run the max value function first. Max will find the maximum value for the particular state. So that will be V. V is the maximum value. It will return the action in successor of state with max value V. Now, how does it selects? How does this value is selected? As we selected 3 there. Which action has been taken? Which was having 3 as the utility, that was action 1. Now, we are selecting that particular action which is having the max value V returned by the max value function. So, how does it work? It will return the utility value, but actually what it is doing, if the state on which we are calculating the max value, if it is the terminal state, so it means terminal test is true. So it will simply return the utility value for that particular state. Otherwise, what it will do, it will take the value as infinity, because it has to now calculate. Utility is not there and it is not given on that level. Okay, so what it will assume? It will assume that the value is infinity. So what it will do now, for A and S in successor state, we are having successor state according to actions. So for action A1, state is S1. For action 2, state is S2 and so on. In our example, we were having 3 states. So for AS in successor state, what it will do? It will find out the maximum of V, the values, okay, and the min value of S. It means here min will work. For this current state, what will be the min value? What min will do? Min will calculate the minimum among the successors. Okay, so successors min value will be calculated. How min value is calculated? By considering the min of V. V is our infinity here, plus the maximum values of S, because what is running below min, that is max. What is below max, that is min. So min will take minimum value from calculated values of max, and max will take maximum values from the calculated minimum value of min. So this way the process will go on until we get the utilities of the state. So this way the algorithm works. It will call the max value function. The max value will call the max of the current V as well as the successors. And what min will do, it will calculate the current V and the maximum values, the minimum among the maximum values returned by max. So this is our utility value that will play the role at end, and it will make it return. It will break the recursive concept, recursive algorithm. Now the properties, if we are having finite tree, then yes, minimax value will give us the result. It is complete. It will definitely give us solution. If we are having finite number of steps, is it optimal? Yes. The minimax play the optimal solution because we are calculating the utilities value, assuming the opponent is playing optimal. It is not returning the suboptimal option. What will be the time complexity? Time complexity, as we are using depth first, we are going to action 1, then action 1 is taking mean value, then mean is taking again max value, and so on. So what it is actually running, the time what it is running DFS, so the time complexity will be higher, that is order of b to the power m, where b is the number of possible successors and m is the maximum possible depth. What about space complexity? Space complexity will be linear. Why it will be linear? Because it is using depth first search, and in depth first search we have to just store the branch which we are currently exploring. Okay, we are exploring the current branch, so its space complexity will be order of bm. That is, linear space is required when we are running Minimax algorithm. Now, can we upgrade it, or can we use it when we are having more than 2 players? Because our game setup was for 2 players. One is max and another one is min. It was designed for 2 players. Now the question is, if we are having a game in which more than 2 players are there, so yes, we can do that. What change will be there? We will give the turns. Let me say 3 players are there, A, B, C. So we'll give one turn to A, then to B, then to C. Again A, B, C, A, B, C. Just we did in 2 ply. That is max, min, and so on. And till we get the utility value, we are going on searching the possible actions. Okay. Now what change you have to make? We have to make, that is, now we will take a vector of values. There we were using just single value because min was minimizing the values of successors, and max was maximizing the values of successor. Now we are having 3 players, so we can't say it is max or min. All are having their try, and they are trying to win the game. Okay. So now let me say A's turn is there. Now it is A's turn. What A is having? A has to maximize its value. So we will take a vector of values. The number of values in a vector will be equal to the number of players. Here we are having 3 players. So what will happen? A will maintain 3 values. First is for 1 to 6. We will maintain 3 values. Now what A will try to do? It will try to find this value. Okay, so if I consider it, what are the values of successors? 1 to 6 minus 1, 5, 2. So A will maximize its designated value. So 1 and minus 1. Which one is better? 1, higher. So 1 is taken here. If we say B's turn, here we are having B's turn. What is B's option? It is having 2 value from this action and 1 value from this action. So what it will take? It will take the maximum value, which is 2. Now if turn goes to C, C is having 2 options, 6 for this action and 3 for this action. So which one is better? Which one is maximum? That is 6 utility. So it is taking 6 here, 1 to 6. So what changes we have done when we are having multiplayer games means the number of players are more than 2. Then we are maintaining a vector of utility values, and every player is trying to maximize its utility. So this is our multiplayer game. So this is all about using the Minimax algorithm for multiplayer game. Further many enhancements have been done on these. So one we will discuss in our next recording, that is alpha beta pruning. Thank you. Jai Hind.